Okay, so let's move into the next section. We're talking about double and half angle identities in this particular section. And you're like, well, what do you mean by double angle? Here's what you need to understand. So far, we've been finding the trig function of single angles. For example, we've been asked to find the sine of theta, right? Now, here's the deal. What's the coefficient of theta? It's a 1, which means that is a single angle. And that's what we've been working with up until this point. But there are going to be times that they may ask us to actually find the sine of 2 theta. And to be honest with you, we don't know how to find the sine of 2 theta. Because when we deal with these trig functions, we are dealing with a right triangle. And the right triangle only deals with a single angle, not a double angle. Because when you recall, when we've drawn triangles and we've labeled one of the angles, we call it theta, a single angle. So this particular section, one of the topics, is going to help us figure out how do we handle a double angle. What do we do with it? Because I really need these double angles to go back to single angles so I can use those right triangles again. Got it? Okay, so let's move into the double angle identities. So the first double angle identity I want to write down is sine of 2 theta. Now again, I don't know how to find the sine of a double angle. Right triangles only deal with a single angle. So I need to reduce this. I need to reduce it from a double angle down to a single angle. And here is the identity that's going to help us do that. This identity, if I take the sine of theta times the cosine of theta and multiply it by 2, that is how I'm going to find the sine of the double angle identity. Or the double angle, I should say. Got it? Okay. The next one, let's talk about cosine. Now, here's the thing about the cosine of 2 theta. This cosine of 2 theta actually has 3 different ways to find it. You're like, well, how can that be? Because the original way to reduce this cosine of 2 theta from a double angle to a single angle, the original identity looks like this. Does that look familiar? It should. It looks like our Pythagorean trig identity, because the Pythagorean trig identity that involves cosine squared and sine squared looks like this. Are you with me? So here's the deal. This is the original way to reduce a cosine of 2 theta down to single angles. Now, I'm going to do a little adjustment to this Pythagorean trig identity, which is how I'm going to get these other 2. So let me, in this Pythagorean trig identity, let me get cosine squared by itself. Do you agree I minus the sine squared on both sides? Good. If I take this cosine of 2 theta, which is cosine squared theta minus sine squared theta, if I take this identity and I substitute cosine squared of theta with 1 minus sine squared theta, so 1 minus sine squared theta, right? That takes the place of cosine squared theta because of the Pythagorean trig identity. And then I minus this other sine squared theta, right? I have 2 terms I can combine, don't I? Which means another way to write the cosine of 2 theta, another way to reduce the cosine of 2 theta back to a single angle is 1 minus 2 sine squared theta. Good? And all we did was we took Pythagorean's trig identity and we solved it for cosine squared theta and then made a substitution into here. Well, by the same token, I have one more way I can find the cosine of 2 theta. And instead of taking Pythagorean's trig identity and solving for cosine squared, I am now going to solve it for sine squared. So let's see what this looks like. So now if I take Pythagorean's trig identity and I isolate the sine squared of theta, that would be 1 minus cosine squared theta, wouldn't it? If I take the original identity for cosine of 2 theta, which was cosine squared theta minus sine squared theta, and I make a simple substitution, the cosine squared theta stays as is, and instead of writing sine squared theta, I write this replacement Let's see what happens. So I have cosine squared theta minus 1 plus cosine squared theta, don't I? Well, looks like I could write this as a negative 1 plus 2 cosine squared theta. Or 2 cosine squared theta minus 1. Either way, it's the same thing. Good? So, because of the original identity that reduces cosine of 2 theta into a single angle, these squares lead me to Pythagorean's trig identity. And if I rearrange Pythagorean's trig identity 2 different ways, that's how I get these other 2 identities for reducing cosine of 2 theta. And some of you may literally want to write cosine of 2 theta on each of these lines, so you're like, oh yeah, that's what these identities represent. So we've got 3 ways of reducing the cosine of 2 theta. Cool? Okay, tangent. Gotta get tangent in there. You know that as well as I do. Because we'll take the tangent of 2 theta, and I'm going to need to reduce that. And it reduces to 2 tangent of theta over 1 minus tangent squared theta. So, the way to reduce sine, cosine, and tangent of 2 thetas are these particular reducing formulas, shall I say, double angle identities. If you need the secant of 2 theta, well, secant's the reciprocal of what? Good, cosine, which means I can choose any of these 3. And once I know what the cosine of 2 theta is, all I have to do is flip it over to get the secant of 2 theta, right? Okay, so those other 3 trig identities are just reciprocals, remember. If you know these, you flip them over and you get the other 3. Cool? Okay, so hang in there. I have some examples for us. Okay, before we get into some examples, I actually want to go over the half angle identities. But I'm going to show you how they're derived. So here's the thing. What we're going to look at is 2 of the double angle identities. And we're going to look at the ones for 2 cosine of theta. So let's look at this one first, and then I'll get to that one over there. So if I look at the 2 cosine of theta, or the cosine of 2 theta, this helps me reduce this double angle to a single angle. Agreed? Now here's what I'm going to do. I'm just going to do some algebra. I want to get the sine squared theta by itself. So, first thing I do is I'm going to move this 1 over. right? Excuse me, I forgot something. Yeah, there's a 2 there, wasn't there? And next thing I'm going to do is I'm going to divide by that negative 2. Agreed? Okay, I'm not going to leave the negative in the denominator, so I am going to multiply top and bottom by the negative, which means these signs are going to end up changing in the numerator. And then I shall end up with the sine squared of theta equals this lovely little fraction. Good? Okay. Here's what I'd like you to notice here. Now I can get sine by itself, and the way I get sine by itself is I'll take that square root. Agreed? But here's what I want you to notice. Do you notice that this is a single angle, and over here is twice as big? That's a 2 theta, right? That's a double angle. It's twice as big, isn't it? So, if I say, and I'm going to take the square root at the same time. If I say that sine of theta over 2, remember I said I take the square root at the same time, right? Okay, now here's the deal. Remember, this angle is a 1 theta. This angle is 2 theta. This is the single, right? This is double it, isn't it? So, if I now say instead half of theta, then under this square root, this is going to have to be, underneath it, twice as big. It's going to be double it, isn't it? And if it's double, that means then that we have just the cosine of theta. Interesting, huh? I need to take the half angles and I need to bring them up to a single angle. And the way we do that is through a simple observation. When we got sine squared by itself from this double angle identity, we noticed that this was your single angle, this was double that. Whatever angle this is, this would be double it. So, in this particular case, if this was half, then double a half is 1. Remember, the square root came from getting rid of the square, so I took the square root of both sides. Are you with me? Okay. Let's look over here at the cosine of 2 theta. I am going to solve this for cosine squared. So when I do that, the cosine of 2 theta plus 1, right? Divide both sides by that 2, and I'll have 1 plus cosine of 2 theta over 2 equals cosine squared theta. Boy, that looks familiar, doesn't it? Again, this angle is a single angle. This angle on this side is twice as big as this angle over here, which means if, and I'm going to take the square root at the same time, if I replace this angle, this theta, and I say the cosine of 1/2 theta, remember, I got rid of the square at the same time, then that means this angle has to be twice as big as this angle. So what's twice as big as a half? Just 1. This is how we get the half angle identities. This is how we get 2 of them. This is how we get those half angle identities. Cool? Okay. So there's one more trig function that we have to find the half angle for, and that's for tangent. So quick refresher of your brain. Tangent is sine over cosine, isn't it? If I take this sine and divide it by this cosine, then the tangent of theta over 2 is going to be plus or minus the square root of 1 minus cosine of theta over 1 plus cosine of theta. Sine divided by cosine. Remember, I'm going to take this and flip this guy over because you multiply by the reciprocal, don't you? Does that make sense? This is how we get our half angle identities. These three right here are your half angle identities. And this is how they were derived. They were derived from the double angles. Cool? Okay, so hang in there. Now I've got some examples for us. Okay, so let's look at this example. The directions say to evaluate and to give an exact answer. So here's what they've given us. They're asking us to take the sign of what's in this bracket, right? Okay, so notice this doesn't say inverse, right? This is just sine. If I look in the bracket, I see a multiplication problem. I see 2 times. And what is the 2 getting multiplied by? It's getting multiplied by this thing, isn't it? Do you notice there's this inverse symbol here? Well, if that's the inverse symbol, then that means a negative 4/5 is what? Your angle or your answer? That negative 4/5 is the answer, which means this whole thing is theta, which means you are really being asked to find the sine of 2 theta. That's what you're really being asked to find, is the sine of 2 theta. Good? Okay, so to find the sine of 2 theta, I have to reduce to get it from a double angle to a single angle. And the formula, or the identity, to reduce it looks like this, doesn't it? Which means I need to actually know the sine of theta and the cosine of theta in order to find the sine of 2 theta. You with me? Okay, so you're like, well, how am I going to do that? Look what you told yourself. You already told yourself what theta equals. You said theta equals the sine inverse of negative 4/5, right? Are the numbers 4 and 5 on the 45, 45, 90 degree triangle? Nope, because remember, that's the answer, right? Are the numbers 4 and 5 on the 30, 60, 90 degree triangle? Nope. Are they on the unit circle? Nope. Which means option 4, you've got to draw your own triangle. So I am going to draw my own triangle. And my triangle is a right triangle. I always put theta here. That's just my consistency. And since they were talking sine, sine is opposite over hypotenuse, right? So opposite over hypotenuse. Remember, the hypotenuse is always positive. And that leaves me to find this unknown side. And this unknown side, using Pythagorean's theorem, becomes a 3. Remember what I've mentioned before. Unless they tell me otherwise, that 3 is going to be positive. If they wanted it to be negative, they should have told me what quadrant we were in, or they should have said that side is a negative side. But they didn't. Good? Okay, so check it out. That means for us to find the sine of 2 theta, I need to do 2 times the sine of theta and multiply it by the cosine of theta. Based upon this triangle, here's my theta. Sine of theta is opposite over hypotenuse, so negative 4/5, right? Cosine of theta is adjacent over hypotenuse, so 3/5. Agreed? Which means the sine of 2 theta is equal to negative 24 over 25 after you multiply these fractions together. What was the key here? The key here was actually understanding this part and realizing that was an angle. And once you knew it was an angle, then you knew you were finding the sine of 2 times the angle, the sine of 2 theta. And then realizing that these numbers, negative 4 and 5, were not on the two triangles or the unit circle, which means we had to draw our own triangle in order to find the sine and cosine of theta, so we could actually simplify, or I should say evaluate this problem. Good? Okay, hang in there. No surprise, I got another one. Okay, so let's look at this next problem. They're asking us to find the cosine of what's in this bracket. So I have recognized that cosine does not have a negative 1 attached to it up here, so we're good. I'm noticing in the bracket I'm taking 2, and again I have a multiplication problem, and it's being multiplied by this thing. Well, since there's a negative 1 there, that tells me this is the inverse, which tells me these numbers here are the answers, which means this is actually theta, isn't it? So we're really being asked to find the cosine of 2 times theta, right? And there are 3 ways of finding the cosine of 2 theta. You could do cosine squared theta minus sine squared, or one of the other 2. I'm going to choose to use the cosine of 2 squared theta minus 1. And you're like, why did you choose to use that? Hang in there. I'll show you. Here's what I know. Yes, I need to find the cosine squared of theta in order to figure this out, right? Here's what I know. We know that theta equals cosine inverse of negative square root of 2 over 2, don't we? Because that's what we said theta was equivalent to at the beginning. Agreed? Which means that the cosine of theta is equal to negative square root of 2 over 2. So here's the deal. If I know cosine of theta, why would I use one of the other identities that asks me to use sine as well? I already know cosine. I don't want to use the identity that says cosine squared and sine squared. I don't want to use the identity that said sine squared and a plus 1. I don't need to use any of the other 2 when I've got cosine already. Why don't I just use the identity that involves only cosine? Are you with me? By the way, there's like 2 other ways of evaluating this problem based on the fact that we're dealing with a cosine of 2 theta. So there's like 2 and 3 other ways. So all I'm saying is this is one way of us evaluating this. And the reason that I chose this particular identity was because I knew theta equaled cosine inverse, which means cosine of theta was already given this value. So the cosine of 2 theta is going to be found by using this reducing identity and taking 2 and substituting in the square root of 2 over 2 squared minus 1, right? Okay, let's get our algebra on here. So this will be a positive number. The square root of 2 squared is? Good. 2. This denominator goes to a 4 minus 1, right? This is 4 over 4 minus 1, which is just 0. So in this particular case, the cosine of 2 theta is equal to 0. Good? I didn't even need to draw my own triangle. Why? Because I already knew the cosine of theta based upon this fact right here. that this cosine inverse was equal, or this cosine inverse was of a negative square root of 2 over 2 was my theta. Okay, so hang in there. Got another. Okay, so let's look at this next problem. They're asking us to use the half angle identity to find the exact value for the sine of 75 degrees. The exact value, once again, the exact answer means no calculator, so stay off of it. So here's what they're telling me. They're saying if they want me to use the half angle identity to find this, then they're telling me that the sine of 75 degrees must be equal to the sine of the half angle, right? Sine of theta over 2. Well, since these are both sine, that means that 75 degrees has to be equal to theta over 2. You with me? Which means theta in this case must be equal to 150 degrees. Cool? Okay, so, 150 degrees. I'm hearing reference angle. Hang in there a second. All right. So my question to you is this. How do I find the sine of theta over 2? The sine of theta over 2 is found by taking plus or minus the square root of, what is it? 1 minus? Let me take a quick look. Yep. 1 minus the cosine of theta, right? We just said theta was 150 degrees, which means the sine of 150 degrees over 2, right? Plus or minus the cosine of 150 degrees over 2. On the left, this would be the sine of 75 degrees, wouldn't it? Over here on the right, in order to figure this out, I need to know the cosine of 150 degrees, don't I? Okay, 150 degrees is which quadrant? Excellent, second quadrant. So if this is 150 degrees, then that's a 30-degree reference angle here, isn't it? And that means that's 60 degrees here, isn't it? Okay, start labeling this triangle. The value of 1 goes opposite 30 degrees. Your radius is a 2. And across from the 60 is a negative square root of 3. Why is it negative? That's right, because you're in quadrant 2, and the x's in quadrant 2 are negative. So the cosine is x over r, so negative root 3 over 2, and then divided by 2. With me? Okay, so we know this is going to be an addition problem, right? In the numerator, let's get our algebra. We're adding fractions, aren't we? 1, couldn't this be rewritten? 1 can be rewritten as 2 over 2 plus the square root of 3 over 2. Do you agree? Okay, which means I would get 2 plus square root of 3 over 2, and we're still dividing by this 2, aren't we? Well, when we divide by that 2, that means you're actually doing what? Yeah, this dividing by 2 actually means you're multiplying by 1/2. Agreed? So this looks like plus or minus the square root of 2 plus square root of 3 over 4. Right? Okay. Can I simplify this lovely little fraction at all? I actually can. Yes, some of you said you can. Some of you are like, I have no idea. Hang in there. I just need a little bit of board space. And I'm going to bring it right here. Okay. Let me rewrite this. The sine of 75 degrees equals plus or minus. Now, this is a division problem, isn't it? Which means it's not glued together, which means I can separate the numerator from the denominator. You know the square root of 4. What's the square root of 4? Yeah, the square root of 4 is just 2. So the numerator I can't do anything with. The denominator is just a 2. And then I have one last question. Is my answer really going to be both answers, both positive and negative? And if you're like, well, remember, they're asking you to find the sine of 70 degrees, right? 75 degrees is which quadrant? Yeah, 75 degrees is here. It's a quadrant 1 angle. And sine in quadrant 1 is positive, which means my answer is a positive answer. Good? Okay, so remember, we found theta. When they told me the sine of 70 degrees, and they said use the half angle, that means sine of 75 degrees had to equal this half angle, which gave us 150 degrees. The sine of 75 degrees is exactly saying the sine is exactly the same as saying the sine of 150 degrees divided by 2. Because 150 degrees divided by 2 is 75 degrees, right? Okay, hang in there. I got another half angle. Okay, so let's look at this next problem. They're asking me to find using the half angle identity again, to find the exact answer for the tangent of negative 7 pi over 8. So, here's the deal. This means if I'm using the half angle identity, then that means that the tangent of negative 7 pi over 8 must be equal to the tangent of theta over 2. Since they're both tangents and it's equal, that means the angles have to be equal to each other. I'm going to multiply both sides by 2, which equals negative 7 pi over 4. Are you with me? So, now that I know what theta I'm working with, that means that I am finding the tangent of theta over 2, again plus or minus, 1 minus cosine of theta over 1 plus cosine of theta. And what did we say theta was? Negative 7 pi over 4. So the tangent of, and instead of saying divided by 2, I'm going to say multiplied by a half. Why? Because it's easier for me to see. Because if I literally multiply these two, I get the negative 7/8 pi, right? Okay, plus or minus square root and cosine negative 7 pi over 4 on both thetas, because that's what we found theta was, negative 7 pi over 4. Cool? Okay. Now, I need to come up with the cosine of negative 7 pi over 4 if I'm going to answer this correctly. So you know what we have to do, don't you? Yeah, we got to go look at the circle, figure out what quadrant negative 7 pi over 4 is in, go find a reference angle for it, all that great stuff. Are you with me? Okay. So now that I've got myself some board space, this will be, I'm going in the negative direction with this angle, aren't I? So here's the deal. That's 0. That's negative pi over 2, negative pi, negative 3 pi over 2, and a negative 2 pi. Correct? Some of you know where negative 7 pi over 4 is located, and some of you don't. So here's how I'm going to get you to actually realize where it's located. I'm going to change every single one of these into a denominator of 8. So this would be what? Negative 4 pi over 8? Or not 8, pardon me, a denominator of 4. I'm sorry, my brain was on the original one. So let's change it to a denominator of 4. So that's negative 2 pi over 4, right? This one is negative 4 pi over 4. This one, negative 6 pi over 4. And this is what? Negative 8 pi over 4 for the negative 2 pi. So if I'm going in the negative direction, negative 7 pi over 4 lands where? Yep, it lands right here in first quadrant. That's negative 7 pi over 4. And what's the difference between negative 7 pi over 4 and negative 8 pi over 4? Yep, there's a reference angle of pi over 4. And isn't that a 45-degree angle? So, we got 1, 1, and square root of 2, don't we? And all those numbers are positive because they're in quadrant 1, correct? So I'm basically finding the cosine of negative 7 pi over 4 is the same thing as finding the cosine of a positive pi over 4 because that's my reference angle. It's in first quadrant, and negative 7 pi over 4 is in first quadrant. Cool? Okay, right here was my key. Labeling these or renaming these angles and putting them into denominators of 4 made it very easy to find where the negative 7 pi over 4 landed. So, little tip for you guys. Okay, so what is this? Square root of 2 over 2, isn't it? So let's get back over here. We have plus or minus 1 minus square root of 2 over 2 and 1 plus square root of 2 over 2. You got to add fractions. So get your algebra going over there. Add your fractions. We have 2 minus square root of 2, the whole thing over 2, divided by 2 plus square root of 2 over 2. And this is so far the tangent of negative 7 pi over 8, right? Remember when you multiply those together. Okay. I'm dividing these two guys, aren't I? So, this is going to be, this top fraction is going to get multiplied by the reciprocal of this bottom fraction, isn't it? Which tells me that I am going to get the square root of 2 minus square root of 2 over 2 plus square root of 2. Now all I need to figure out is if that answer is a positive answer or a negative answer. It can't be both. It has to be one or the other. And if I know what quadrant that negative 7 pi over 8 is in, we'll be good. Okay, so 2 ways of doing it. Here is negative 7 pi over 4. If I take half of it, which quadrant do I end up in, right? Or what I could do is I could relabel these. This guy would be, I relabel it in terms of eighths. This guy would be what, negative 4 pi over 8? And pi would be negative 8 pi over 8. Well, I think I found the quadrant. I think it's a quadrant 3 angle. This is a quadrant 3 angle. And if this is quadrant 3, tangent is going to be positive. Because y over x, both y and x and y are negative, and the two negatives divided by each other will give me a positive. Cool? Okay, so on this one I suggest pausing and going back and replaying it just to make sure you caught all the little nuances. There was a lot going on here, especially because it was in radian measurement. I really had to pay attention to this circle and where the negative 7 pi over 8 landed and where the negative 7 pi over 4 landed. And that was relabeling or making these typical angle measurements into the correct denominator so I could see where each of these angles lied. Good? Okay, so hang in there. Got another problem for us. Okay, so let's look at this next example. They say, given that f of x is the sine of x, they would like you to find f of 2 beta. You're like, what's beta? Well, they gave us this nice little drawing. And on this drawing, they gave me a circle. And they basically have told me the equation of the circle is x squared plus y squared equals 74. Boy, doesn't that look like Pythagorean's theorem? X squared plus y squared equals r squared? Good. Let's keep that in mind. They told me beta was in second quadrant. And they gave me this point x, comma 5. Okay, so let's think about this a second. What are they asking me to find? You are really finding f of 2 beta, right? Well, what is f? Yeah, f is sine of x, isn't it? So f of 2 beta is going to equal the sine of 2 beta, right? Because this basically told me x and 2 beta were the same, weren't they? Well, looks like I'm trying to find the sine of 2 beta. Looks like I'm trying to find a double angle, aren't I? And I don't know how to find a double angle. I have to reduce it to a single angle. Good. Which means this is 2 times the sine of beta times the cosine of beta. So I need to know the sine and cosine of beta. Woohoo! Well, since I'm on a circle, to find sine and cosine, we need x, y, and r, don't we? Do you know x? Nope. Do you know y? Yep, you know it's 5. Do you know r? Remember what we said? X squared plus y squared equals, yeah, this is r squared, isn't it? Which means r is equal to the square root of 74. That was nice of them. They actually gave me r. They hid it, but they gave it to me, didn't they? So it looks like I need to find x. How are we going to find x? Good. I'm hoping some of you said just use this equation. So x squared, y is 5, right? Which means x squared plus, good, 25. Get the x squared by itself, that's good, 49. And then you take the square root, and how many answers do you get? You get 2 answers. You get a negative 7 and a positive 7. And the question is, which one of those x's is the one we're going to use? Yeah, this is quadrant 2, isn't it? And in quadrant 2, x is negative. Good? Okay, so let's come back over here. Let's see what this looks like. So I have 2 times the sine. How do you find sine? Y over r. And some of you are going, shouldn't we rationalize that? Just hang in there. Cosine, x over r. Agreed? Okay, so I multiply the numerator. I get a negative 70. What's the square root of 74 times itself? Yeah, 74. That's why I didn't rationalize it, because it took care of itself. Cool? Okay, which means that f of 2 beta is equal to negative 35 over 37, because you had to reduce the fraction. Good? Okay, hang in there. I got one more problem for you. Okay, let's verify this identity. Remember the ground rules. You can't move anything from one side to the other, and you can only work one side at a time. So what side do you want to work on? If you're like, oh, I'm not sure. I personally am going to work on the left. Why? Because I see a subtraction problem. I see two terms. The right side only has one term, and I'm like, well, there's not a whole lot I can do with that. So over here on the left side, what I'm noticing is I have a difference of two squares. Aren't they? They may not actually be a power of 2, but 4 is a multiple of 2, isn't it? So, couldn't I factor this? Let's see if you see the factoring. So since it's a difference of squares, I have one of those parentheses with cosine squared minus sine squared, and I have the other parenthesis with cosine squared plus sine squared. And yes, a theta. I get a little lazy like you, and I forget to say my theta. Okay, so, wait a minute. Cosine squared theta plus sine squared theta is what? Yep, by Pythagorean's identity, right? Pythagorean trig identity, which means I've got the cosine squared of theta minus the sine squared of theta times 1, don't I? And cosine squared theta minus sine squared theta, yeah, that's one of the new identities we just looked at. This is actually representing the cosine of 2 theta, which, looky there, equals the cosine of 2 theta. Check! Well, that was nice, wasn't it? Cool. All right, you have fun with this stuff, and I'll catch you on the flip side.